Hello everyone, welcome to this AMD Vivado tutorial. In today's video, I'll explain the complete AMD Vivado design flow. So we'll start from the Vivado home screen and understanding each steps involved in developing an FPGA design using Vivado. So by end of this video, you will have a clear understanding of the entire workflow. So from creating a new project, adding a design sources and constraints, running a simulation, a synthesis, implementation, and timing analysis. Finally, we generate the bit stream. So this video is designed to give a complete overview how a design moves through the Vivado tool. Understanding this workflow will help you confidently work on a FPGA project using AMD Vivado. So the home screen is divided into several sections like a quick start, task, learning center. So each of these sections serves a specific purpose and helps us perform different activities in the Vivado. So for this video, our focus will be on the quick start section because every FPGA project begins here only. So the other sections are also useful, but they are mainly used during the specific stage of the design process. So as we move through the complete design flow in a later stage, I'll explain sections whenever they become relevant. So let's understand the purpose of each one. So the first option is create a project. So this option you will use whenever you want to start a new FPGA design. Clicking a create a project launches a new project wizard, so which guides you through the creating a new project. And here you will specify the project name, choose the project location, and select the target FPGA device or development board, and configure the project setting also. So in simple terms, every new FPGA design in Vivado start with a create project option. Then open projects. So the second option is the open project. Suppose you have already created a Vivado project. You want to continue work on it later. So instead of creating a new project, you will simply click open project and browse to the project directory and open the existing project. And the third option is open example project. So AMD Vivado includes a collection of built-in example projects that demonstrate various design techniques, IP codes, and FPGA design methodologies. So these example projects are an excellent resources for beginners to learn from working a design, and for experienced user to understand a specific features or IP are implemented. So here, after clicking new project, so new project wizard opens. So this wizard guides us through the steps required to create a new Vivado project. Now let's click on next to continue. So in this step, we need to enter the project name, choose the location where you want to project will be saved. So the project name, identify your project. You can enter any meaningful name here. So here I'm using my project. The project location specify where the objects files will be stored on your computer. You can type a path or click the browse button to select folder. So I create a simple on desktop. I'll create one folder, my project. So keep the create project subdirectory option checked. This create a separate folder for your project and keep all the project files organized. Once you have entered the project name and location, just click on next. So this window allows us to choose the type of project we want to create in Vivado. So different project types are available for different design requirement. Let's briefly understand each option. So here RTL project, use it to create a new FPGA design using a Verilog or system Verilog. This is a post-synthesis project, use it to analyze the design after synthesis. And IO planning and project. So use it to plan and assigning FPGA inputs into like input output pins. And imported projects, here this option is used import an existing project into the Vivado. And example project. So use it to create a project from predefined example provided by this Vivado. So now I'll select RTL project. So it's selected by default anyway. So for most of the FPGA design project, we will select RTL project option, as it supports the complete design flow from RTL coding to the bitstream generation. Do not specify source at this time. So option is checked by default. So this allows us to create the project first, and later we add the design files. If you already have a design files, so you can uncheck this option and add them during the project creation. So remaining project types are intended for specific purpose and are used only when required for this tutorial. So we'll keep the default setting RTL project and do not specify the source at this time. Just click on next. So now we need to select FPGA board or a device here. So we'll use this board for this project. So Vivado needs this information so it knows which hardware we are targeting. So at the top you will see two options: parts and boards. Parts and boards. So if you know exact FPGA part number, you can select it, and from the part tab, and you are using FPGA development board, it's easier to use the board tab. So Vivado automatically picks the correct FPGA device for the selected board. So here you can select the list of boards available in the Vivado. For this tutorial, I will select here Zinc Ultra Scale. So different, select. So this one I'll select. Zinc Ultra Scale ZCU10 evolution board. We have this board in our lab, so I'll select this one. For example, a few boards are not listed here. That means the board files are not installed. So you can download from your board vendor, or maybe from GitHub, and add them to Vivado. I will show another separate video how to add the board files to this Vivado. Also, if you are just learning Vivado or only want to generate bitstream, you don't have select a development board, just you can simply choose the required FPGA device from the part tab. Once you selected the board or device, click next to continue. So this is the last step. Here Vivado display a summary of your project setting. Check the details once and then click finish to create a new project. So once you click finish, Vivado create the project and opens the main workspace. From here, we'll perform all the steps of the FPGA design flow, including adding sources, simulation, synthesis, implementation, and finally we generate the bitstream. Now if you look at the left hand side of the Vivado window, you will see the flow navigator. So this is where we will spend most of our time while working in a Vivado. So it shows the complete FPGA design flow in the order we will follow. Let's quickly see what each option is used for. So this project manager is where we manage our projects, add designing files, and change the project settings. And this IP catalog is used to add pre-designed IP codes to our projects. And IP integrator, let us create a block design by connecting IPs graphically by using this IP integrator. And we'll do a simulation. So it is used to verify our design works correctly before implementing it onto the FPGA. And RTL analysis helps us view and analyze RTL designs here. And the next one, synthesis. This convert our HDL into FPGA hardware logic here. And implementation maps the design onto the FPGA by placing and routing it. So programming and debugging is used to generate the bitstream and program the FPGA and debug the design on hardware. Don't worry about all these options right now. So we will use each one as we go through the FPGA design flow. Now look at this source window. So this is where you will find all the files that belongs to your project. As you keep working on your design, this window will be updated automatically. So these files are grouped into different sections: design source, constraint, simulation source, and utility sources. So this design source is where you write a Verilog and system Verilog design files will appear here. And the constraints, so is where you will find the XDC file used for pin assignment and timing constraints. And the simulation source contains the test bench files used for simulation. By default, Vivado create a simulation set called a sim1. So utility sources store any additional information additional files that may be needed for the project. At the bottom, you will see the 3 tabs: hierarchy, libraries, and compile order. So these help you view the design hierarchy and libraries are being used and order in which the source files are compiled. Don't worry if this window looks empty right now. So as we add design files, the constraints files and test bench files, they'll automatically update here. So if you see, this is the project summary window. It gives us a quick overview of the project, including a project name, selected FPGA device, and other basic settings. As we run synthesis implementation, their status will displayed here. So making it easy to monitor the progress of the design. At the bottom, you will see a few tabs. So we will use throughout this project. So the TCL console shows the command that Vivado runs in background, and a message tab. So display the information, warnings, and any errors that occur. And this log keeps the record everything Vivado does during the project. So here the report tab, it contains the report generated after synthesis and implementation. So finally, the design runs tabs shows the status of synthesized and implementation. So you can easily check whether they are running or completed. So we will use these tabs whenever we need them during the FPGA design flow. So this properties window, wherever you select any file or object in the project, so details will be displayed here. Since we have not selected anything yet, the window is empty. So now let's add sources to our project. So there are 2 ways to do this. So here in the project navigator, so we have one option like add sources. The second method is used to source window. Simply here I need to add the design source now. For example, so design source, just simply click on plus icon at the top. So right click inside the source window, select add sources. Now we click design source and click like this. So now we'll get a new source wizard. You can use this to add new source files. So since we want to add our design files, let's open the add source wizard and continue. So I want to create a design source. I'll click on this. So in this window, we want to ask us type of source you want to add the project. We have 3 options. So let's briefly understand each one here. So add and create design sources. So this option is used to add our design files, and add create constraints. So this option is used to add and create XDC constraint files. So constraints files define the FPGA pin assignment, clock information, and other timing constraints required for our design. And add or create simulation sources. So this option is used to add or create test bench files. These files are used only for a simulation to verify the design works correctly before implementing onto the FPGA. Since we are adding our RTL design, so we will select add or create design source and click onto the next. So in this step, so we need to add our design files to our project. We have 3 options here. So add files, add directories, and create files. So this add files, use this option if your Verilog and system Verilog files are already available on your computer. Simply click add files and select the required files. So add directories here. So if, for example, if all your design files are stored in a folder, so you can use this option to add the entire directory instead of selecting a file on one by one. So next one is a create file. So if you don't have any design file yet, you can create a new Verilog or system Verilog files directly from the Vivado. So in this example, I will click create file and create a new Verilog source file. So after clicking create file, so this dialog box appears. So first select the file type. So here we have so many options: Verilog, system Verilog, VHDL, and other things. So I'll select a Verilog here. So I'll choose a Verilog. So you can select VHDL or system Verilog if you require. So next, enter the name of the file. So now here I'm giving simple off order. Off order is my file name. So I'll name it off order. So we'll keep file location as the default. So we save the file inside the project folder. Now click OK to create the file. Now if you see, we are getting some file here, offorder.v. I'll just add one input port. So now, for example, if I So now the module name is off adder. So here I need to add some input ports and output ports also. So you can add here, or you can later you can add in that Verilog file also. So now if required, you can add all remaining inputs outputs here. Otherwise you can define them later in the Verilog code also. So just I'll give one port name off adder, just one port input name, the port name named as A. It is the input. So now okay. Now see here updating. So now if we check here, so this offadder.v is added under the design source tab. Now I click on it. So now here, so here I can write my Verilog code. Just right. So here I am writing a code. We want to check syntax automatically correct. So now just here my intention is to just explain the Vivado design flow. So just I'll take a simple offadder code here. Just I'll okay. So now, so this is my module offadder, contains 2 inputs and 2 outputs, sum and carry. So these are the assign sum A XOR B, assign carry A and B. This Verilog code describe the offadder. So here I am writing the Verilog code. So Vivado checks syntax automatically. If there is any syntax error, you will notice a small red. For example, instead of this blocking, if I use like non-blocking, now you will get a red line here. So here also we'll get some red color box here. So these red marks on the right side of the editor, this indicate there is an error somewhere in your code. For example, have intentionally written an incorrect statement operator. So Vivado highlights it as an error. Once I correct the syntax, so this red mark, for example, if I remove this one, so now red mark disappeared, indicate that code is now free from the syntax error. Notice the green indicator on the right side. So this tells us that the code is free from the syntax error. Just you can save. Once you finish the writing code, you can press Ctrl S to save the file, or you can save file here from here. You can select the save button from this toolbar. So if you see an asterisk next to the file name, it means the file is not saved. So press Ctrl S to save the file. Once it's saved, asterisk disappear. Now it disappears. Now that we have created our RTL design, the next steps to verify whether it's worked correctly. So before implementing the design on FPGA, it's always good practice to simulate it. So to perform simulation, we need to create a test bench. So a test bench is a Verilog module that applies a different input values to our design, and we observe that outputs. So this helps us verify that the RTL behaves as expected before moving to the synthesis and implementation. So let's create a test bench for an offadder design. So now here, go to the simulation source, select simulation source. So now this RTL design is also added under the simulation source tab. It is also available in the design source. Now this, until we add the simulation source, this offadder acts as a talk model. So now we are going to create a test bench for our design. So in the add source, so select add or create simulation source. You can create simulation source, or else you can use this plus button. Okay, add or create a simulation source. So click onto the next. This option use it to add the test bench files of the project. Now we have successfully, now I create a file. So this is a Verilog. So this is my test bench TB. Okay, then finish. So now this is the TB. Okay, the test bench does not have any input output. So just okay, click it. Now we'll get this test bench is updating in the source window. Now we'll get TB here. So now I want to edit this more. Okay, I'll take a test bench file of order TB. Just I'll so now this is my test bench file. My intention is to understand the Vivado design flow, not Verilog here. Just I'll get simple test bench for offadder. So now we have successfully added the test bench file to our project. So you can see that it appears under the simulation source section in the source window. This tells us we want to recognize it as a simulation file. So now see the name of this instantiation UUT. So now it will appear here UUT. So we have finished the writing a test bench. Next we will use this test bench to simulate RTL design and verify its functionality. So now that our RTL design test bench are ready, let's simulate the design. So there are several ways to generate input stimulus to the test bench. So for this example, I use a simple test bench with predefined input values just to understand the Vivado simulation flow. So to run the simulation, go to the flow navigator and on the left hand side and click on the run simulation here. So then select the run behavioral simulation. To run the simulation, you go to the navigate flow and click on the run simulation and select the run behavior simulation. So now Vivado now compiles both RTL design and test bench. If there are any syntax error, compilation error, so they will be displayed before the simulation starts. Once the compilation is successful, Vivado automatically opens the simulation environment where we can observe the waveforms and verify the outputs for our design. Now see here. So if A is 0, B is 1, then sum 1, carry 0. Now if we select like this, A equal to 1, B equal to 1, sum 0 and carry 1. So now let's look into the RTL schematic here. This is a graphical representation of your Verilog design. So it helps us to understand how Vivado has interpreted our RTL code. As you can see, the off order is implemented using XOR gate and one AND gate. So this confirms that our RTL design is correct. So now here we'll see the schematic of our RTL design. Now see, it contains one AND gate and its XOR gate. So now this off order is implemented by using this XOR gate and AND gates. Now that we have verified our RTL design, the next step is to run synthesis. So to do that, click on synthesis. The next step is to run the synthesis. To this, you can click on synthesis. So during the synthesis, now if you see, observe the running synthesis design we are getting here. So during this synthesis, Vivado converts our Verilog code into hardware implementation. So that can be mapped onto the selected FPGA device. We targeted initially while creating a project, we selected one board or a part. So we are targeting that FPGA board by selecting this. So it also checks the design any synthesis errors and generates the reports and such as a resource utilization reports and the timing information. It takes some time to synthesize this. So depending upon the size of design, the synthesis may take a few seconds or few minutes. So our synthesis here completed successfully. So we'll open a design, see our design has been implemented. So open synthesis design. So once synthesis completed successfully, so we'll open synthesized design and see our design has been implemented. So let's open the synthesized design. So the schematic here, if I open the schematic, is different from the RTL schematic we saw earlier. So this RTL schematic showed the logic that described in our Verilog code. So the synthesized schematic shows how Vivado has actually mapped our design onto the targeted FPGA. So here you can see two lookup tables, LUTs, and these lookup tables, which are the basic building blocks or elements inside an FPGA. So Vivado has implemented XOR and AND logic using LUTs, and you can also see some input buffers and output buffers. So IBF stand for input buffer. It connects external FPGA input pins to the internal logic. Similarly, output buffer. So now it stands for output buffer, OBUF. So it connects the internal logic to the external FPGA pins. So this schematic gives us a view of how a Verilog design is actually implemented inside the FPGA after synthesis. So the next step is implementation, where the Vivado plays and routes this design onto the FPGA device. On the left hand side, you will see the netlist window also here. So here see nets and leaves. The nets nothing but voids we can connect here. Now see here, if A buffer, if you select, so here, so carry some. So we have some leaf cells also. So in this netlist window, it shows synthesized component our design. The first icon here shows the nets. The net is a simple connection wire that carries the signal between the different components in the design, just like a wires connected components in electronic circuits. nets connected to the logic elements inside the EAPCET. So if you expand the nets folder, you will see all the signal connection created during the synthesis, and then continue the leaf cells. So the next section here, leaf cells. So these are the basic hardware elements that Vivado is used to implement the design. So such as LUTs are input buffer and output buffer. Expanding this folder shows all the hardware blocks used in the synthesized design. So far we have learned how to create a project and had the RTL and test bench files, run a simulation, perform RTL analysis, and complete synthesis. However, the FPGA design flow does not end here. There are still a few important steps remaining. So first we will learn how to create a constraint file, also known as XDC file. So in this file, I will assign FPGA pins, define the clock, and specify other design constraints. So without a proper constraint file, the FPGA won't know which physical pins to use. So next we will run the implementation step. During the implementation, Vivado plays the logic onto the FPGA resources and routes their connections. After implementation, we'll generate a bit stream. So the bit stream is a final binary file that contains the FPGA configuration. So this is the file that is downloaded onto the FPGA board. So finally, we learn how to program the FPGA using a hardware manager. We'll connect the FPGA board to the computer and open the hardware manager and download the bitstream onto the device. Once the programming is completed, so our design will start running onto the FPGA. So we will cover all these steps in detail in the next video.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.